let's jump into the topic of synthetic data generation for RAG evaluation. So, with RAG evaluation, we could, pass some questions in to the LLM with RAG and then look at the answers and then decide on ourselves whether or not we think things are working okay. But it's not, one, that's not really scalable. Two, you're not really having measurable numbers that you can actually improve on, because you can only improve what you measure. So that's where synthetic data generation comes in. So I'll just show you this image we have going on here that kind of showed what we did and how we generated those questions, how we made sure those questions were diverse, how we made sure those questions were grounded in real evidence that were using chunks that were inside our RAG pipeline essentially. And then overall, how did our RAG pipeline perform? So to build that synthetic test data set, you could start off, well, in the example we went through, we started off with a PDF. Just like normal RAG, you chunk and then chunk it and then embed it in a vector database. You add a bit of metadata. So the metadata initially added in that chunking phase would be like page content and document metadata. So things like page number and so on, or chunk size and whatnot. And then from there, we take those chunks and pass it into a RAGAS pipeline. So RAGAS is like a RAG assessment framework. It's pretty common in industry, and within these are the steps that happen. So we start off with a summary extractor. So this is an LLM looking at the chunks and then providing a summary for that. So here we made 20 pages chunked nicely, and so we have 20 LLM calls that then add a summary on as a data field. Then from there, in parallel, on all those chunks, we then run an embedding extractor, theme extractor, and something called an NER extractor. But all in all, what they're doing is it's kind of getting out the themes and the entities for those chunks. So once we have all that information, we can start to kind of enrich those chunks. We can add themes, we can add entities, we can also start to connect the chunks. So in our example, we connected using both cosine similarity, but then also an overlap score builder, which looked at the theme and the entity of the chunk. So we had kind of you could say we were looking at two kinds of relationships, where cosine similarity showed similar embeddings, whereas themes and entities kind of covered similar topics. So even if they didn't use similar language, with a cosine similarity would be kind of poor between two nodes, but they were both touching on the same thing, well then that overlap score builder we would get an edge, kind of showing that there's an entity overlap between the two nodes, even though their cosine similarities would be poor. And what this all turns into is pretty much a knowledge graph. And yeah, once we have that knowledge graph, the next thing we do is that we can pass our graph into what we call synthesizers, or essentially LLMs, and then from there we can generate different kinds of questions by referring to different chunks. So the questions might be single hop, where it's kind of a very basic question like, oh, what is the average lifespan of a cat? Straightforward, single number. There's probably a single chunk within our knowledge graph that can be pulled and answered that question directly. And then from there we can also generate questions that might be multi-hop specific. So this would be kind of like a question that would require a bit more research and a bit more depth into finding an answer. And that one might be something like, if a cat is vomiting, what would be the symptoms and how would we treat these symptoms? And is there anything we can do to prevent a cat from getting sick in this manner? So we're kind of asking a multi-threaded question. To answer that kind of question, we would have to pull many chunks, do many hops to different chunks to kind of answer our question. And it's not so straightforward like the single hop. And then a multi-hop abstract one would be questions that also require multi-hopping to get to them, but they're more focused on themes. So that might be, what are the symptoms? A cat is sick, and how does I guess in our scenario we had a specific PDF. How does our feline document touch on this? So you're kind of answering a multi-layered question, and it's going more towards themes and less towards more towards like an abstract question that's more open-ended rather than like a specific symptom, cause effect, multi-hop scenario that I just explained before. So we can see that here in the workbook. I'll just scroll through quickly. So touching on single hop, multi-hop, specific and abstract. An important distinction to make when we're building those questions is we can come up and we can synthesize things in different distributions depending on, say, our use case. So if we expect our LLM to be used by doctors and they will ask probably very specific questions, well then maybe you would want your synthesized data set to have more multi-hop specific queries and maybe single hop specific queries and maybe slightly less multi-hop abstract questions. And so that's something you can change as well. I think in this example I just went with 33, 33, 33, so a third broken up. And here you can see kind of the input question that was generated, references, and then the synthesizer name, so whether it's single, multi-hop, abstract, specific, and then also the kind of answers that would be generated. I'll just scroll through here. Yeah, this is a good view. So we've got our question, and then our reference context, and then a reference answer that would be generated. And then using this, we've kind of got a database to evaluate our RAG against, where we've got a question, reference context pulled, and then answers. An important thing to note here is it's important to review what the LLM generated. Make sure there's no duplications, make sure the answers and the context that is used to answer the questions all kind of lines up and makes sense. You can see here I reviewed all 6 questions that were generated, and in the end I think I decided to remove the last one because it was focusing on like Hazel C. Carney, who was an author, but there's no direct link between what was asked and Hazel, and so it was probably just too confusing and wasn't being answered with the right references, and so removing it was the best option in that case. Whereas here in this row 4, I decided to edit the question and so an answer, just because one, the wording was so and a little confusing, and then the answer was so as well. So it's always good to double check your work and not just trust the LLM blindly. So moving on, we then have essentially our question, answers, and context, and then using that we can test our RAG pipeline. So in the RAGAS framework that was used, the metrics we focused on were answer correctness, answer groundedness, and retrieval relevance. So answer correctness, whether the generated answer versus our answer that we generate, and then answer groundedness, whether the generated answer retrieved context that was kind of grounding its answer, because I guess in different industries, making sure your LLM isn't kind of deviating or making ungrounded statements or providing misinformation to users is very important. And then whether the context retrieved was relevant to our input question. So moving on, we can see here that to kind of get these values, we use LLM as a judge. So essentially we're using another LLM, and that LLM is focusing on giving us a score for that given metric. Okay, so we ran a baseline experiment where we had initial chunking of 500 characters and a retrieval of k equals 3, and you can also see here the chunk overlap was 75. And I'll just show you what those results looked like. So I can take you here where we have our input, our reference outputs, and the actual outputs that our RAG pipeline generated. So initially we can see that the answer correctness, groundedness, and relevance on average was okay. And down here at the very last question, which is actually the one that we edited, we can see that the answer correctness performed very poorly. But is that a problem? Well, we can inspect it. And looking at the actual output that the LLM generated for our question, I'll just show you the question. How do these guidelines use individualized risk assessment and an individualized lifelong healthcare strategy across the cat life stages, and so on? And then looking at the output, we can actually see here that the LLM states, however, the corpus does not provide enough information to explain in detail kind of what was asked in our question. And that is good LLM behavior, because this is what we specify in our system prompt, where we say if you don't have enough information, state that you don't have enough information. And so adhering here and essentially giving us a poor answer correctness is fine, because the behavior of the LLM is correct in this scenario. But obviously things can be improved. In the next experiment that we performed, we increased k to 6. So rather than retrieving 3 top candidate chunks, we retrieved 6. So essentially more information is being passed into the LLM before it gives its final answer. And we can see those results here. You can see overall there was actually a bit of an improvement. We went from 0.45 to 0.55, so we could say that, and we can see whether or not it was actually able to answer that question. And so by giving it more chunks, it's probably better. Giving it more chunks, it's better able to answer questions because it's retrieved more context and more information to help it answer those questions, which is kind of expected. And we also start to use more tokens when we increased K because we're adding more chunks, which is consuming more of the context window. And so I've got a bit of a table here that kind of shows the changes overall across those 3 metrics that we're focused on. And yeah, you can see here that generally overall things did increase. However, on row number 4, there was a slight decrease in the retrieval relevance. This was interesting because I guess you're adding more chunks, which is kind of diluting the information that's there. So the relevance of that retrieval context is lower, but overall the answer correctness increased at the same time. So I would probably say it's okay leaving K equals 6 in this scenario. And so I kind of made that the new baseline to work off from. And then the next experiment done was increasing the chunk size from 500 to 1,000. But we kept the same chunk overlap and all the other variables were the same. This is important because then we can attribute the change to only changing that one variable, the chunk size. So yeah, we remake the vector database and so on and increase the chunk size to 1,000. Then we rerun our evaluation and we can see that here, still green. There was a slight decrease in the average answers. I'll show you a summary table soon and talk to some specific examples. So here we can see that the answer correctness, there was a slight decrease on average, and the gradness slightly decreased, but the relevance, a tiny increase, I would say, overall. And then because of increasing the chunk size, we're giving, more how would you describe by increasing the chunk size, it's essentially there's more information being fed into the LLM and the RAG pipeline, and we can see I thought it would actually improve the answers overall and improve things because more is better, but in this scenario not so much. Then inspecting a few of the different examples that were run in this scenario here, an interesting one to point out was that for single hop in one of the single hop specific queries where it's very straightforward, there was actually a decrease across the board in our metrics, whereas for abstract queries, multi-hop abstract queries, there was an increase in the correctness and retrieval relevance, and then the groundedness remained at the same for our row 5 example. So I think with increasing the chunk size, what we actually did is, well, yes, we're providing more information, but by providing even more information, we're getting better at answering abstract questions in our RAG pipeline, but this doesn't necessarily improve answering single hop specific queries where they're very straightforward. They would require a single chunk, and you're kind of diluting and maybe making giving too much context to the LLM that it's not able to answer the question so succinctly, and so that's probably why we see this decrease here. So I think my biggest takeaway from all of this is this single paragraph here where it's really important to understand the use case of the RAG application and the type of questions we expect it to receive, because we can see that changing different things, we may be better at answering some questions than not others. But also, for example, if it's maybe just what is my star sign or something more ephemeral, we probably don't need to worry about groundedness as much. But if we're working in, say, the medicine industry or finance, we need hard facts, and that has to be heavily grounded first and foremost. So I think in our scenario, definitely more experimentation, maybe more resources provided to the RAG pipeline to help answer different questions. There's a whole list of changes that we could do, but all in all, this was an interesting experimentation and goes to show that a lot can be improved. Thanks for listening.